Yes, so I guess you can hear me. I've waited extra 5 minutes, so we can just proceed. Okay. Please just give me a thumbs up if you can hear me.
I can hear you, but it's breaking.
Sorry, come again.
I can hear you, but the line breaks.
Okay. Any different opinion? Okay.
I think
So,
it's fine now.
okay. So let's see. It may be from your internet. Well, let's do a recap of weight, and then the what we've done so far, so we can just proceed from there. Okay. So we are basically looking at chemical reactions, and then we mentioned few of them. So we mentioned number one, we talk about the combination reaction. And the combination reaction, we said that it's the same as saying the synthesis of a compound. So the combination reaction basically is when we have a compound A reacting with compound B to form a compound AB. We cited an example of that as well. Then I also mentioned the reverse combination. And the reverse combination is basically known as a decomposition. So decomposition. Okay. And that has to do with we having a compound AB, it decomposes to produce A plus B. Then we mentioned that it depends on the type of compound that we have. If it is just a binary compound, then that compound can decompose into forming two elements, where the molecules of this element or that element, it can also decompose to form just one compound and then one element. But if it is a polyatomic or what we call a tertiary kind of a compound, well, that's a tertiary compound. Then we are looking at the tertiary or the polyatomic compound. Then we are looking at having just one compound and then one element producing after that decomposition, or we can have two compounds being produced at the end. Then, of course, we also mentioned substitution reaction, or what we call replacement or displacement reactions. So replacement, displacement, substitution reactions. And that we mentioned that we can either have just one element being substituted, or we can have two elements being substituted. So the double displacement, single displacement. The double displacement is also known as the metathesis, or what we call the exchange reaction. So we are just exchanging elements. Now we understand that some of these elements are quite active than others. So if you look at the most active element, then of course, considering it's like metals or non-metals, then for metals, we look at the alkali being the most active, followed by the alkaline. Okay, that's a group 1. Then the group 2, we can also see aluminium We can see manganese, we can see zinc, we can see chromium. We can see manganese. Please mute your mic. Mute your mic or I take you off.
Please,
Okay, so the Bui guy, I'm going to mute you, but then if it happens again, I'll just remove you from that. Okay. If it happens again, you mute yourself, then it means that you are just here to disturb the class. And so you just have to leave the class. Okay. Yeah, so we are looking at just most active elements. And so the metals, the group 1, group 2, the group 3, which is the aluminum. Then we can also have the iron. And then so we can have tin, we can have lead, we can have hydrogen being followed by that group. Then we can have copper, we can have silver, and the least kind of active element will be, well, in the series, that will be the gold. Now, for most active non-metals, we can talk of decreasing down. So we can have fluorine, can have oxygen, we can have chlorine. Well, chlorine will be in a par with that. Then, of course, we can have the bromine, we can have the iodide, the gases. So for substitution reaction, the basic concept here is that we understand some element are most active than the other. And so the most active element will go to displace, replace, or substitute the less active element. So for example, aluminum can't display a chromium in a chromium compound. So when that is just one element going to displacing the other, that will say that that is just a single displacement. Now, if it looks like one is displacing the other and the other is also displacing the other one. So we cited an example, for example, this acid-base reaction where we have sodium hydroxide engaging, say, ACl. We understand the sodium, which is the alkali, is quite reactive than the hydrogen, so it will displace the hydrogen, and then the hydrogen also attaches itself to that. So that becomes the sodium chloride plus the water. I hope you are following that. Those that are muting their mic to just stop. Okay, I guess some people are just on the platform to just come and disturb. They are not really interested in the class, and so I guess I have to block some people from the class. They are not interested in the class. Yes, I've seen a hand there. Okay, so that's what we did for the displacement or the replacement reaction. We also mentioned the combustion reaction, which is also known as the burning. So burning a substance in air. Well, if that substance is an inorganic substance, we produce the oxide of that substance. If it is an organic compound, we are going to be producing carbon dioxide and water. That is for complete combustion. But for incomplete combustion, then we are looking at having carbon monoxide and then water. That is for incomplete combustion. So that's just what we did. And so we also introduce ourselves to the precipitation reaction. So the precipitation reaction to precipitate. So precipitation reaction, which has its own driving force from the double displacement reaction. So that's basically looking at the aqueous solutions, and that if you have an aqueous solution, what it means is that the compound in that water is just going to be in this ionic. Please, are you asking a question? Okay, I guess some of you don't hit to warning, so I just need to take some of you out. Yes. So what's the problem? Okay. So that's a precipitation reaction, and that has to do with we having compounds that are soluble in water. So we call that the aqueous solution. So for precipitation reaction, we are looking at the how a compound will just dissolve in water and then will create ions. So we mentioned that once you are going to be creating ions, they are going to be creating what we call electrolytes. That's that possibility of allowing electricity to pass through them. Now we can have what we call the strong electrolyte, weak electrolyte, and then the non-electrolyte. Okay, the strong electrolytes are those that can completely dissociate in water. So they completely dissociate into the ion forms. That's you have the cation, full cation, and then the full anion. We mentioned that ionic compounds are found of completely dissociating. I mean, most of them dissociating in water. Then strong acids, strong bases also dissociate completely in water. So this can be the strong electrolyte. Then we can have the weak electrolyte, which are going to be like weak bases, weak acids that will dissociate partially. So they don't dissociate fully, but partially. So we'll use the arrow which shows like that so that we know that this is partial dissociation. Okay, so they dissociate. That means that they are not into full ions, and so they will allow flow of electrons. They will allow flow of electrons partially. Well, that's just so the non-electrolyte will just be those that are full of molecular compounds that does not have charges in them. For example, sugars and those stuff. So these are the non-electrolytes. So let's really look at what we mean by precipitation reaction. Now, as I mentioned, we are going to be having sorry. Okay. I can't hear you. Okay. So let's move on. So we are still looking at that precipitation reaction, and that we have kind of ions coming together, and of course the ions will be in their aqueous form, so they'll be in their charges form. Yet when different ions like a cation and then anion comes together, instead of them still being in the aqueous forms, you see them forming solids. So for example, we know of kidney stones. I don't know if you are aware of kidney stones. Please, have you heard of that?
Yes.
Well, basically, this will be like
Yes, sir. Yes, sir.
okay, so these are just like calcium carbonate or so and this basically forms precipitates which settle down and sometimes it hardens and becomes so hard. Now the question will be that how do we form these precipitates? Well, we are able to form this precipitate because we have some rules that governs us that when particular type of cation meets a particular type of anion, then instead of them being soluble in water, that is, instead of them being aqueous, they become soluble. Well, this rule is basically what we call the solubility rules. Well, solubility rules, and these are just rules. Some write more rules, but then I just want to summarize that into just six rules, so that we'll put everything under the 6 rules. So the solubility rules basically is just going to be helping us to predictions. So we are just basically going to predict how these ionic compounds can be aqueous or can be solid. So they say where we want to predict whether it's going to be aqueous or it's going to be solid. And this is the rules that governs us to be able to know that this. So I'll group the rules into 2. There are 6, but then I'll group them. Well, some write more than 6, meaning they will break them down more so that you have more rules. But just for easy way of remembering that, I just use 6 and then I'll group the 6 also into 2, where I'll talk of those that are soluble and then those that are insoluble. Okay, so those that are soluble are those that can easily dissolve in water and those that will not dissolve. And those that will not be dissolved will be what we call solid. Those that will dissolve will be what we are calling the aqueous compound. I said earlier that you are mute, you just because I'm not looking at the board. So if you have any question, just unmute and then talk. Otherwise, you drop your hand if you have raised your hand. So I'm waiting.
Okay, sir.
Yes, I'm listening.
Thank you guys have a bad day.
Is if you are not asking a question, mute yourself. If you're asking a question, let us hear you. Well, I don't think maybe you want to answer a question. So 2 parts. The part 1, we are looking at those that are soluble. And then the part 2, we are looking at those that are insoluble. That means that those will easily form solid. So the ionic compounds that can form solid and the ionic compounds that will be in the aqueous form. Now, aqueous basically means they are in their charges. Now, we understand that ionic compounds are basically cations and then anions put together to form a compound. This is what we are calling the ionic compound. So we should know the cation part, we should know the anion part. And when we put the 2 together, it's either still going to be in their ionic form. And when I say ionic form, what it means is that they are still, the aqueous form, meaning they are still in the solution form. So I give you an example before I give you the rules. Say, for example, if I have, say, sodium hydroxide, well, this sodium hydroxide basically in water will be sodium and then the hydroxide. Basically, what it means is that the sodium will be in water, which is aqueous. Hydroxide will also be in the water that is aqueous. And so this compound is going to be aqueous. Okay, so that means that they are in their charge form. Now let's look at these rules and then see if we can remember them. Well, for the part one where we are talking of the soluble compounds, the first one that I'll mention is that when I have the group 1 metals, and of course, example of these group 1 metals are lithium, sodium, potassium. So that's group 1. Those have +1 charges. And I'll include ammonium because ammonium behave like the group 1 metals. While compounds of these cations, that's a group 1 metals, and then the ammonium are generally soluble. There are no exceptions. These are soluble compounds, no exception. There's no exception. So when you see compounds which has, say for example, sodium hydroxide, once I have sodium there, that compound is aqueous, is soluble. There is no exception to that. I hope that is clear. Now, another thing or another rule is that if we have compounds like nitrates, so compound that has nitrate in them, that's the anion is nitrate. Compound that has acetate in that, so acetate are also going to be soluble. Such compounds are soluble. Again,
Yeah,
there's
the
no.
writings are not appearing.
Please confirm from others. It's not true. So please check your internet or check your phone if you are using laptop. The others can confirm if it is not true because I can see that. I'm monitoring it with a different phone. So once my phone is showing, it means that it's coming from your end. So here, there are no exceptions. So for example, if you have, say calcium nitrate, well, this is going to be aqueous. It's going to be soluble. No exception. So all nitrates, all acetates are generally soluble with no exception to that rule. Is that okay? Number 3 is that when I have the halogens, and of course, because of it, the reactivity of fluorine, we don't normally engage that. So compound that has these halogens, chlorine, bromine, then the iodine, or the iodide, that's a halide, are also soluble. So such compounds are soluble. That means that they will be in the aqueous form. But this time there's an exception to that rule. The exception is that when any of these halides comes into contact with cations such as lead 2+, mercury 2+, and then silver plus. Well, silver will be slightly, so it will be slightly soluble, but then still insoluble. So when they come into contact with these 3 elements, they become insoluble. That means that they become solid. So for example, lead chloride. If you have lead chloride, this is going to be soluble. So that's going to be solid. If you have, say, for example, silver bromide, this is also going to be solid. It's going to be insoluble. Otherwise, all the compounds that you're going to be you find this halide there, they are going to be soluble, meaning they are going to be aqueous. So for example, if I have, say, barium chloride, then that is going to be in aqueous form, meaning it is just going to be barium 2+ plus 2Cl-. Please, is that okay?
Sir.
Yes.
Please, what about gold?
Good what? Good chloride. Sorry, where am I writing?
Yeah.
So that
Gold.
is going to be aqueous. So gold
Sir,
chloride, so gold.
Sir, what about barium sulfate?
Come again.
What about barium sulfate?
I've not mentioned sulfate. So why are you bringing sulfate?
So the gold plus any of those anions will form an aqueous solution.
Yes. So there's no, the only exception is that when this halides come to contact with lead, mercury, and silver. Silver is slightly soluble, but then it's still insoluble, but then slightly soluble. Then they become solid. They become kind of insoluble. Is that okay? So let me view this. Okay. So that is the third rule. Well, we can also look at another rule here. Now, anions such as the sulfate, anions such as the sulfate are generally kind of, they are generally soluble. They are generally soluble, except when they meet with those that has +2 charges. So they are generally soluble, except when they meet with, say, calcium 2+, barium 2+, of course, lead is also 2+, mercury is 2+, and of course, silver is also captured here. So silver plus, which is also slightly soluble. So sulfate is generally kind of soluble, except when they meet with calcium 2+, barium 2+, lead, mercury, and then silver, they become insoluble. Okay, so that means that if I have, say, calcium sulfate, then this will become a solid. If I have barium sulfate, that is solid. But then if I have, say, potassium sulfate, then this is aqueous. If I have other metals like sodium, whatever, of course, the group 1 there are going to be. So if I have, for example, H2SO4, H or will be soluble, so this becomes aqueous. Are you following? Okay.
Yes, sir.
Yes, sir.
So,
Yes, sir.
well, I'll give you the
Sir.
rules and later I'll start giving you the compounds to predict their solubilities or, yes.
So that means sodium sulfate is
I'm barely hearing you. What are you saying?
I said sodium sulfate is aqueous.
Sodium,
Sulfate.
yeah, sodium sulfate. Well, if you remember the rules, group 1, all group 1 metals are going to be soluble. So this is aqueous. Even when you don't know at the anion. And of course, we are saying that sulfate is also going to be soluble. So this is purely aqueous compound. Is that okay? Yeah, we can then look at the remaining 2, which is the insoluble systems. Where do I mean that? As showed this.
Sir. Yes, sir.
Yes. Yes, I can hear you if you want to talk. So let me clean this up. Let me clean this part. Yes, I thought you are saying something. Okay. Now let's come to the insoluble rules. Now, for insoluble rules, we can also continue with other kind of anions So anions such as carbonate. So the carbonate, the phosphate, okay, carbonate, phosphate, this is 2. Carbonate, phosphate, chromate. The chromate is CrO4 2 minus. Oxalate, C2O4 2 minus, are generally insoluble. So these are compounds of these anions are going to be insoluble. Can you tell me the exception? Except what? Well, except when they meet with the group 1, you remember there's no exception there. So except when they meet with that group 1 metals and then ammonia, then they become insoluble. So that is the exception. Is that okay? Okay. Is somebody asking a question?
Sir,
Yes.
so that means sodium carbonate is insoluble.
So yes, so sodium is even from group 1. And so when
Yeah.
it meets with carbonate, that becomes insoluble. That is aqueous kind of compound. Are you okay?
Yes, sir.
Okay. Yes. So that's the exception. So when it meets with that group 1 and then ammonium, sorry, I've written ammonium, then that becomes soluble. Well, another rule is that when I have so the hydroxides, if I have hydroxide, if I have sulfide, if I have oxides, and then the other, so the binary kind of anion. So if I have hydroxide, sulfide, oxide, these are generally insoluble. These are generally insoluble. Well, except when it meets with except when it meets with group 1, it becomes soluble. And of course, ammonium, it becomes soluble. And then here again, those that are having the +2 charges, it become soluble. So that's the rules here. So we can group them into 2, where we have those that will form soluble compound. That is, if I say soluble, it means that it's going to be aqueous. And then if I say insoluble, it means that it's going to be solid. Now, how do I know that a compound can be soluble? That is, how do I know it can be kind of aqueous? Well, if I follow that compound, and of course, we're talking of ionic compounds, and that's if the cation there is coming from group 1 metals and then ammonium, then that compound basically is just going to be aqueous. It's going to be soluble. There's no exception. So if group 1 meets with any anion, which you can talk of, it's going to be aqueous. So you can just list all the anions which you know, the common anions that you know, they are all going to be aqueous. Number 2, the nitrate and then the acetate also, when it meets with any cation, then that is also going to be aqueous. That's going to be soluble. That again, no exception. So nitrate with any metal will still be aqueous. is going to be soluble. So it can easily dissolve a nitrate compound. Okay. Then we move on to the halide. So the chlorides, the bromide, the iodide are also soluble, well, except when it meets with lead, mercury, and then silver. Then it becomes insoluble. So that's where we get the soluble kind of compound. Now, those that are insoluble, well, did I mention the sulfates? I think I wrote the sulfate somewhere. Okay, so sulfates are also going to be soluble, except when it meets with the, I think I've gone down. So except when that sulfate meets with those that are having the plus 2, that's calcium, barium, lead, mercury, and of course silver. And silver will just be slightly soluble. So silver sulfate is slightly soluble, but then it's so solid. You can still have some solid not dissolving. Now, if I have anions like carbonate, phosphate, chromate, oxalate, those compounds that they form are going to be solids. That is, they are going to be insoluble. Well, the exception is that, for group 1 metals and ammonium, no exception. So when they meet with the group 1 or the ammonium, then they will become soluble. Then hydroxides, the sulfide, oxide, cyanide, well, when they meet, they are generally going to be insoluble. That means that they are going to be solid, except when they meet with a group 1 and ammonium. And this time, when they meet with group 2, they become kind of soluble. So, for example, if you have calcium hydroxide, then calcium hydroxide is just going to be soluble. Is that okay? But then if I have, say, gold hydroxide, then of course gold hydroxide is just going to be solid. So that's how we get to have that. So if I have, say, zinc sulfide is going to be solid, because the sulfide is generally soluble. The only exception is when it meets with group 1 ammonium or the group 2 metals. Yes.
Sir.
Yes.
Sir. Is sodium acetate is a soluble substance or insoluble?
So sodium is belonging to group 1. So there is no exception. So sodium, even coming closer to acetate to form sodium acetate, makes it aqueous. And of course, the acetate itself is also aqueous. No exception. Are you okay?
Yes, sir.
Okay. Now, from this rule, which I guess you can remember that, meaning once I give you a compound, you should be able to predict what will be the state in terms of whether it is going to be aqueous or it's going to be solid. For other phases, which is the liquid and then the gas, then these are pure kind of state. So molecules comes in their form. So gases, you see molecular compounds becoming gases, and of course they also becoming liquid. But then in terms of ionic compounds, we can either get it to be in the aqueous, or we get it to be in the solid form. Okay, so let's see. So I'm going to create another page here. Let's try to give the phases. So for example, I have NaCl plus silver nitrate. So sodium chloride plus silver nitrate. Now, of course, sodium is quite reactive than silver. And so this is double displacement reaction. So that we're going to be having the sodium nitrate plus the silver chloride. Now let's try to predict the state of this compound. So sodium chloride, what do you think should be the state?
Aqueous.
So that is aqueous because sodium is in group 1. And of course, even that the chloride also is soluble, so nothing will happen. How about this one? Silver nitrate. Yes, silver nitrate. Aqueous or solid?
Solid.
Please. Aqueous because nitrates have no exception.
Yeah.
So nitrate, acetate are generally soluble. There's no exception. Okay. How about silver nitrate? I mean the sodium nitrate.
Aqueous.
Aqueous. How about
Yeah,
silver chloride?
Solid.
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 Well, how did we get that? We said that chlorides are generally soluble except when it meets with lead, mercury, and silver. So this is a precipitate. So silver chloride is solid, and so we'll call that the precipitate. So in other words, what is happening is this. Sodium chloride is this form. So sodium chloride is just sodium and chloride in the solution, plus silver nitrate is also going to be aqueous. So that's a silver ion plus a nitrate ion, which is also in solution. And when you combine them, you're going to see that you're going to form sodium. So the sodium nitrate is going to be in aqueous form, plus the nitrate is still going to be in the aqueous form. But then you are going to be forming silver chloride as a solid substance, which will be depositing below as a precipitate. Okay, so if you look at this reaction, we can say that the sodium really didn't do anything here. Then the nitrates also didn't do anything there. So the resultant ionic equation basically will be like the chloride, which is the aqueous, plus the silver, which is aqueous, now combining to form the silver chloride, which is the solid. So this is the resultant equation, or what you call the overall equation, the overall ionic equation. Okay, now what do I mean by they didn't play a role here? Sodium and then the nitrates. Well, such ions or such a kind of species, we are calling them the spectator ions. They are just there to cheer the reaction. So we call them spectator ions. So they don't actually form part of, they will still be in the aqueous form. So sodium and then the nitrates are just spectator ions. And then the real guys will be the chlorides and then the silver. Let's predict more. How about lead nitrate? Well, that's lead 2. Lead nitrate plus potassium chromate, even as, so this is the group 1 is quite reactive. So that's exchange. So the potassium will exchange with the lead to take the nitrate. So we're going to have the potassium nitrate plus the lead now taking the chromate. Of course, we can balance the equation, but that's not our focus here. Now let's predict that. Lead nitrate, is it going to be solid or is it going to be aqueous?
Solid.
Aqueous.
Aqueous.
I don't know why you are still not following the rules. Nitrate, acetate are generally
Solid.
soluble,
Solid.
no exception.
Solid.
Make an obey that so
Aqueous.
can solid.
Okay, nitrate. They have no
So nitrate, acetate
aqueous.
are generally soluble,
Aqueous.
no exception. They are generally soluble, no exception. Group 1 metals and ammonium are generally soluble, no exception. Halides, that is the chlorides, bromides, iodide, are soluble except when it meets with lead, mercury, and silver, just 3 metals. Otherwise, any metal it meets, it is just soluble, aqueous. Sulfates are generally soluble except when it meets with the calcium, that's the +2 metals, calcium, barium, lead, mercury, and then silver, that's slightly soluble. And so silver sulfate is slightly soluble. That means I still be solid, but then slightly it can dissolve. That is for the soluble stuff. The insoluble part will be carbonate, phosphate, chromate, oxalate are also generally insoluble, except when it meets with the group 1 or ammonium. Then the last part will be the oxides, the hydroxide, the sulfide, and those kind of anions are also going to be insoluble, except when it meets with the group 1, group 2, and then, so when it meets with the group 1 and then group 2, that becomes soluble. So we have nitrate here. Nitrate has no exception. So that is aqueous. How about potassium chromate? Solid or aqueous?
Solid.
Solid.
It's aqueous.
Is this going to be difficult?
No.
Potassium is group 1. Potassium is group 1. Look at the cation and look at the anion before you make the conclusion. Chromates are soluble, except when it meets with the group 1, it becomes, it's insoluble, but when it meets with the group 1 or ammonium, it becomes soluble. It becomes aqueous. And potassium is group 1. So that is soluble, aqueous. Potassium nitrate, solid or aqueous?
Aqueous.
Aqueous.
Okay. How about the lead chromate now?
Solid.
Yes.
Solid.
Well, how did we end up saying it is solid? Well, chromates are all going to be insoluble. The only exception is that if the chromate comes into contact with group 1 or ammonium, and this is not group 1. So this is going to be insoluble. So again, we can write the ionic equation for that. Okay. Well, just as I mentioned, the other state, whether or not a compound is solid or, is gas or liquid, we can't really predict that, but then they come in their molecular kind of form. So let's move on there. So if I have
Sir.
a compound like this,
Hello, sir.
plus HCl, now forming NaCl plus ACl. Yes, is somebody asking a question?
Sir.
Yes.
Sir. Can semi-metal and non-metal form a soluble? No, insoluble compound.
I don't get you. Semi-metal, what is semi-metal? You mean
Like
metalloid?
Acid, yeah, arsenic and oxide.
Arsenic oxide is not a semi-metal. Arsenic is a metal. So arsenic oxide is an ionic compound. It is not a metal. a metalloid. Arsenic is a metal, so it's even classified as a heavy metal.
Sir, I think
Okay, so
Example like
So
maybe
so if you are looking at arsenic oxide, so for example, arsenic oxide, then definitely we are saying that oxides are soluble. There's no exception except when it meets with group 1 and group 2, it becomes, they are insoluble except when it meets with the group 1 and then group 2. So oxide of all the metals are going to be solid. So for example, iron oxide, this is going to be solid. Aluminium oxide, bauxite is going to be solid. So arsenic oxide is going to be solid. The one that asked the question, is that okay?
but I think arsenic is metalloid.
You think?
Sir,
Yes,
yeah.
instead of mentioning my name, just let's talk.
According to the table, arsenic is metalloid.
According to which table?
The periodic table. They have both metal and
found that
properties and
price.
metal properties.
Yes, but I'm saying that we are looking at it becoming a metal-like. So that's why I'm saying that arsenic oxide is treated as ionic. Now, I'm sure we understand what a metalloid is. It can behave like a non-metal, it can behave like a metal. And arsenic behave more like a metal. So we treat it as like a heavy metal. If it gets into water, we call it a metal. So depending on the compound that it forms, then it becomes either a non-metal or it can become a metal. So for example, if I have arsenic chloride, now arsenic chloride, now the arsenic there becomes a non-metal. So that's where it's metal, it becomes like 2. But then if it is oxide, it is now behaving like a metal. Metalloid behave, that's why I call it a semi-metal. Does it make sense?
Yes, sir.
Okay. Now let's predict these states that I've written there. So I have sodium hydroxide. What do you think will be the state? Sodium hydroxide, what's the state? So that is going to be aqueous. Why? Because this is group 1. The sodium is group 1. Of course, there's no exception to that, even though hydroxide will be insoluble, but when it meets with a group 1, it becomes aqueous. How about the HCl, hydrochloric acid? Is it going to be solid?
Aqueous.
So that is going to be aqueous. Why? Because the chlorides are generally soluble. The only exception is that when it comes into contact with lead, mercury, and then silver. And hydrogen is not lead, is not silver, it's not that. Now, how about this one? The sodium chloride.
Aqueous.
Aqueous.
Aqueous. Yes. Well, the water is in its molecular form, so we can say that it's either liquid or it can be a gas. So that's just that. So we can predict the state of these compounds. So once we get that, means that going forward, whatever equation that we write, we should be able to tell whether it's going to be in the aqueous form or going to be in the solid form. So if I have a compound, for example, iron sulfate, what do you think will be the state?
Aqueous.
Yes, come again, you said?
Aqueous.
Aqueous.
Yes, and what was the rule? The rule is that they are generally going to be soluble. Sorry, is somebody asking a question? Okay.
Yes,
So
please.
the sulfate is going to be soluble, except
Yes,
when
please.
it meets with that calcium. Yes. So you can talk.
Please, is calcium hydroxide like, does it have the property of like the solubility and the insolubility?
Of course, that is ionic compound, calcium hydroxide.
Yes.
So predict what do you think will be the state? Is it going to be soluble or insoluble?
I
The
think
one that
if it is soluble, then it means that it depends on the amount of water that we add to the compound.
no, please. Just the compound can tell you whether it is going to be soluble in that water or not. Now, calcium, so if you look at the rule, the hydroxides are generally going to be insoluble, except when it meets with a group 2. Calcium is group 2. So such a compound, if you put it in water, it's going to be dissolved.
Okay.
So if you have asked that question, that okay. So that is that. So we
Okay,
can
sir, please, I
predict.
want to ask a question.
Yes.
For the no, sir, please come up small.
Okay, I was writing something. Okay, yes.
So the sodium chloride.
Mm-hmm.
We said it's aqueous. We said it's aqueous because of the sodium and then chlorine too. But why is it that for the water, we didn't say that it's aqueous, but we wrote it as liquid? But aqueous means that it can dissolve in water.
Well, we are not saying that aqueous is coming from aqua, and aqua can be a mixture of acids. So we have aqua regia. It can be acids and then water. So basically, it's not just like water. So at a point when this becomes well, for molecular compounds, it comes in their own form. So that's why we are saying water is liquid and not aqueous. In other words, if we want to predict it as ionic compound, which we know this is not ionic compound, water is not ionic compound. But if you want to treat water as ionic compound, then definitely this will be aqueous because oxides and then the group 1. But then because water is not ionic compound, we treat it as molecular compound. Now this molecular compound comes in their form as their pure forms, as liquid or as gases. Are you okay?
Yes, please.
So we can only predict for this ionic compound, those that have the charges, that's the cation and then the anion part. That's those that we can predict for. Well, let's look at the last part and last prediction, and then I can then proceed. So I was writing barium chloride plus potassium sulfate. Well, that would be a metathesis or exchange reaction. So we can have the potassium chloride plus the barium sulfate. Let's try to predict the state. So barium chloride, is it going to be solid or aqueous?
Aqueous.
Aqueous. Chloride,
Yes.
the only exception for chloride will be lead, mercury, silver. How about potassium sulfate? Well, since I have potassium there, it's going to be aqueous.
Aqueous.
And so this is going to be aqueous. How about barium sulfate?
Aqueous.
Well, sulfates are soluble except when it meets with the charge 2 groups, calcium, barium, lead, mercury, and then silver. So this is going to be solid. So in case I form that solid, then I've been asked to write, say, the ionic kind of equation. definitely you're going to see that the chloride will be a spectator ion, potassium will be a spectator ion. So the overall ionic equation will be just having the potassium plus and then the chloride minus, sorry, the sulfate rather. So well, the potassium and the chloride are the spectator ions. So it's going to be the barium 2 plus a sulfate to produce the solid, which is the barium sulfate, which is the precipitate, which is going to be forming. Does it make sense?
Yes.
Okay.
Yes.
So that is the precipitation reaction. But another reaction that we can consider, and of course we are familiar with that, is the acid-base reaction, which we call the neutralization reaction. So when we have an acid and then we combine that to, so the next reaction which we are considering is just the acid-base reaction. And the acid-base reaction, we also call it the neutralization reactions. Okay, the neutralization reactions. And that means that, of course, we know from the Bronsted-Lowry definition, acids are compounds that have hydrogen which they can easily donate, and bases will be those that can accept these hydrogen. So in this neutralization reaction, we are looking at just a transfer of hydrogen from one end to the other. So that's the acid-base neutralization. I've cited much example even at the double displacement. For example, HCl is an acid, it meets with NO3, and that will form a salt in water. So for neutralization reaction, the product is a salt which is found in water. Why? Because the acid is aqueous, chlorides, no exception, sodium, no exception, sodium, no exception. And of course, this is pure form, so it can be in the liquid form or in the gaseous form. So in neutralization reaction, we can have the salt in that water. Another example, if I have the sulfuric acid, and then I mix this sulfuric acid with, say, ammonium, what do you think will be the product? Strong acid, weak base. What will be the product?
Ammonium sulfate and
So
plus
we're
water.
going to have the ammonium sulfate, which is the salt. And of course, we know that it is in
Plus.
water because ammonium, no exception, will form a soluble compound. So we know this, the aqueous, of course, it can be aqueous or it can just be liquid. And then this is aqueous. And then we'll also see where, because it's a strong acid, strong base, a gas will be evolving. We are not much interested in the gas, but then we are interested in the salts that will be forming in that water. How about this? So NH3 plus MgOH2. What will be the product?
Magnesium nitrate. Oh.
So there's exchange. Magnesium exchange that, and so we're going to have magnesium nitrate. So let me rewrite that. So we're going to form magnesium nitrate. That's a salt, and that magnesium nitrate will be in water. Okay, so in acid-base reaction or neutralization reaction, when we mix an acid plus a base, so the summary is that in neutralization, when we have an acid plus a base, we are going to be producing a salt, and the salt is in water. So the salt is in water. Now the name of the word salt basically is just compound that contains cation and anion. So they have the cation part and then the anion part, of course. That means that it should be an ionic compound. So for example, salt, the common salt that we have, sodium chloride, it has a cation and then it has the anion part, which is that salt. That's what we call the common salt. So in neutralization reaction, basically you see that it falls under the double displacement, where one is trying to displace the other. Eventually you end up producing a salt in water. Yes, I've seen two hands there. If you have questions, just unmute. After that, mute yourself. Yes.
Okay, sir. I was asking if it means all ionic compounds are salt or
Yes.
okay.
Yes, I've seen another hand. VC. Who is that? What's the full name? Who is that VC? Vero Wahine. Vero Cruz. Who is that Vero Cruz? Okay, I think your hand is already there. So that's a neutralization reaction. Now let's move on to another reaction, which we call the reduction oxidation reaction. Well, that we can shorten it and say reduction. We can have what we call red, and then the oxidation is ox. So we call it the redox reactions. Now so it is two different reactions which are happening simultaneously. So we can have what we call the reduction, reduction reaction, and then oxidation reaction. So let's try to explain these reactions. Now, we have a reaction which involves movement of electrons. Now, in reduction reaction, we are talking of a reaction where a species is gaining electrons at the end of it. So you look at what we are starting at the reactant side. So for reduction reaction, the reactant, after the reaction to the product, will gain extra electrons. That means that it becomes more negative. So where, say for example, the reactant was 0, at the end of the reaction becomes -1. That means that it is going through reduction reaction. I hope it makes sense. Now for oxidation reaction,
Yes,
we are going to
please.
be losing electrons. Instead of, in the reduction, you are going to be gaining electron. In oxidation reactions, we gain electrons at the end of the reaction. So if the reactant is say 0, then at the end when it forms the product, you see it becoming plus, more positive. So in reduction reaction, we'll see that we'll be creating more positive kind of stuff. And so when you put these two reactions and that these reactions happen simultaneously, then we'll say that we have a redox reaction going on at the same time. I mean, redox is reduction, oxidation reaction happening at the same time, where one species is losing, the other species is gaining. And this is quite important because everyday life will see this redox reaction going on. For example, you are using your phone or your laptop, and of course, here in the laptop, they have programmed that and they have calculated the level of electrons that you need. They have calculated it and then they've scaled it to percentage. So you see your phone draining, meaning your electrons are being lost because the electricity is just flow of these electrons. So if you are draining, then you are losing electrons. Then you put the power charger there, then you begin going through reduction. So when it is draining, we'll say that oxidation reaction is happening. When you begin charging it, then reduction reaction is happening. So it's quite important when it comes to our electronics, we use that as that. Well, I don't know if you've tried this when we were young. You just cut pieces of paper, just tear pieces of paper, then you rub a pen on your head for quite some time. Then you drop the pen closer to the paper and then it gets stuck to the pen. Have you tried that before?
Yes, sir.
Okay. Yeah, so
Yes,
that's
sir.
electrostatic force. So basically when you are rubbing it in your head, so normally we want to get the student that don't put those that don't put cream in their hair, dry hair. So you can dry the pen, get rid of all the electrons which is surrounding the pen. And then the paper that you turn are having electrons around. So once you bring the pen closer, there's going to be exchange of electrons. And that's why the paper kind of draw closer to your pen. And so in redox reaction, let me lower it down a little. So in redox reaction, what happens is that we are going to have a species which is going through reduction. And that species become more negative. And then we also have another species that is going to be becoming more positive. That is the oxidation reaction. Okay, so if I have a redox reaction, then what is happening is that I'm going to be having a species which is going through reduction. At the end of it, that species, so, well, let me put plus here. There's also another species which is going through reduction. Well, at the end of it, the species that was going through oxidation becomes
Sure.
reduced. Then the yes. Somebody talking. Okay. Then the species that was going through the reduction will also be oxidized. What do I mean? What I mean is that, say, for example, this was A plus. At the end of the redox reaction, it becomes more negative. And then this was say minus. At the end, it becomes more positive. So there's a species that is causing another species to either lose or gain. So we say that that species is an agent of something. Okay. So if, for example, this species which is causing this kind of compound to lose electron. So it is causing the compound to lose electron. That's why at the end, it becomes oxidized. So it is causing the compound to lose electron. Well, the process of losing that electron is what you are calling oxidation reactions or oxidation process. So that agent that is causing another species to lose electron and that it goes through oxidation is the agent that causes oxidation. So we call that the oxidizing agent. So the oxidizing agent or compound or species will be the agent that causes another compound to lose electron. By effect, what it means is that that agent itself, so this oxidizing agent causes one species to lose electron and goes through oxidation. By effect, at the end of it, that species is going to go through reduction. So oxidizing agent will be the agent that causes oxidation, but then in effect, that species will be kind of reduced. It will be gaining the electron. Now, the reverse is also true. This species is going to cause this species to go through reduction. By in effect, if you look at it, itself it will be going through oxidation. So that species that is going to cause the other species to be reduced is called a reducing agent. In effect, that reducing agent is going through oxidation reaction, meaning at the end of it is going to be more positive. The oxidizing agent at the end will be more negative. Am I making sense?
Yes.
So there's no confusion here where, I mean, sometimes people find it difficult identifying which one is the oxidizing agent, which one is the reducing agent. I don't think it's a problem. The oxidizing agent is, in effect, it will be going through reduction. But then because it is causing the other species to go through oxidation, that's why we are calling it the oxidizing agent. Let me put it this way. So let me clean this one and then put it this way. So in a redox reaction, we have two species there. We have what you call the oxidizing agent. So we have the, of course, where I can say reducing agent plus the oxidizing agent. Okay. Well, it is called reducing agent because it is causing reduction to happen. So it is causing reduction to happen. But in natural sense, at the end of it, is that a question? So at the end of it, this species is going through oxidation. And then this species is going through reduction. So it will become more negative. Okay, and then here it will become more positive. But then because it is an agent that causes that, we'll say this is an oxidizing agent or a reducing agent. Well, this phenomenon is quite interesting because just as I mentioned, our galvanic cell, voltaic cell uses redox reactions to just so electrolytic cells. Well, basically our electronics basically uses the flow of electrons from one end to the other end. So if I take the phone again, there are some apps which are causing the battery to be drained. So that app is basically causing oxidation to happen. So the apps becomes an oxidizing agent. In other words, the app is taking your electrons. So the app itself is going through reduction. It is taking the electron. It is going through reduction. But then it is causing your battery to lose the electron. Is it making sense?
Yes,
Yes,
sir.
sir.
Yes.
Okay, so at least from our previous studies, we know how to calculate the oxidation state of elements in a compound so that we can know that from one end to the other, we can know the differences that is happening there, whether it is going through oxidation or it is going through reduction. So for example, if I have, say, Fe, well, solid, and then at the end, I'm producing Fe2+, what do you think is happening? Is it going through oxidation or reduction?
Electron minus.
So from
Reduction.
Fe and
Reduction.
Fe is 0, that is solid. So the oxidation state here is 0. And then here the oxidation here is +2. So what is that process?
That is reduction.
Oxidation.
Please,
Oxidation.
it's not reduction. You are losing electron. Can't you see from 0, you have lost electron. Again,
Can't
don't
you see?
forget that when you are losing, you are becoming more positive. And when you are gaining electrons, you are becoming more negative. So this is basically an oxidation reaction. So we are losing. That's why I put here so that I'll balance the equation. So I only put here the 2 electrons just to balance the electrons. But actually what is happening is that I'm taking the electrons from this kind of stuff. So this is oxidation reaction. Now, can you tell me this? Say Cl minus now becomes Cl0. What do you think is happening?
Reduction.
Oxidation.
Oh,
Oxidation.
it's oxidation.
Reduce
Hey, please. We are having extra electrons. You have taken the extra electrons. Now we have 0. So we are becoming more positive. That is oxidation, not reduction. Well, let me give you another example. Maybe that one you get. So say, for example, I have Cl2, and that Cl2 becomes Cl minus. What is happening?
Reduction.
Are we losing or are we gaining
Reduction.
electrons?
We are losing.
So this is
Yeah,
reduction.
Reduction.
So when we are gaining electrons, that becomes reduction. Is that okay?
Same.
So the half equation, so this is what we call half redox reaction. So for example, if I put them together and I say Fe plus Cl2 moving to Fe2 plus Cl minus, you can see that if you separate them into their half reactions, you can separate them and see Fe moving to Fe2 plus, and then Cl2 moving to Cl minus. We have separated them into their half reactions. And that you see that this one is going through oxidation. And then this one is going through reduction. Do you agree? Do you agree,
Yes,
please?
sir.
Yes.
Okay. So we separate the rate. So because they are happening at the same time. So this is their half reaction. Okay. So can you identify the oxidizing agent in this case? Which one is the oxidizing agent? Which one is the reducing agent?
The oxidizing agent is CO2.
The chlorine gas is the oxidation.
So the chlorine gas here is the
The
oxidizing agent.
Agent.
It is causing the oxidation, but then itself it is going to reduce.
Reduction.
Then the ion here will be the reducing agent. Is that okay?
Yes, sir.
But the reducing agent is also called the reductant. And then the oxidizing agent we call the oxidant. So it's just a name that way. So basically how we can do that is to be able to calculate the oxidation state for each element and then know whether from one point to the other it has gained electrons or it has lost electrons. So there it has already been calculated to know that ion is 0 here, it moves and become +2. So it has lost 2 electrons. The process of losing electrons basically is just the so the process of losing that is the oxidation reactions. And then the process of gaining. So if you look at the chlorine here, it is chlorine 0. Now it becomes -1, meaning you have gained electrons. And so you become, it goes through the reduction reactions. Does it make sense?
Yes, sir.
Okay.
Yes, sir.
Now, the most kind of important thing that we want to kind of derive here is that we should be able to balance the reaction. So in redox reaction, our interest here is to see how we can balance this equation. Okay, so how do we balance this equation is quite interesting to us. Otherwise, in redox reaction, what you are just seeing is that we are having a species which is losing and then another species which is gaining. The species which is causing the oxidation to happen is the oxidizing agent, and the species which is causing the reduction to happen is the reducing agent. So at the end, the oxidizing agent is being reduced. That means that at the end, the oxidizing, the oxidizing agent is going to be more negative. Then the reducing agent at the end will be more positive. It's going to lose electron. So, but then it is causing reduction to happen. It makes sense. Okay. Now, our role here is to be able to figure out whether a species is going through oxidation or another species is going through reduction. And then we'll try to see if we can balance these species. So that's the most important part of the redox reaction. So we see that they are happening at the same time. So we try to see if we can balance this equation. Now, trying to balance this equation, we have to be able to separate these equations into their half reactions. And if I say half reaction, we should be able to separate the reactions into the oxidation and then the reduction reaction, so that we, after separating that, we can balance this equation separately, and then we'll bring this equation back to the original form. So again, I take the Fe, so Fe plus Cl2 moving to Fe2 plus Cl minus. Well, if you check the equation, it is not balanced. How do I balance it? Well, I can only balance it if I separate them into their half reactions. So their half reactions will be Fe moving to Fe2 plus, and then Cl2 moving to Cl2 minus. So these are their half reaction, oxidation, reduction reactions. Then the next step is to balance the individual half reactions separately. How do we balance them? We balance the elements first. Then the second is to balance the charges. Balance the element, balance the charges as the second step. Now, how do we balance the charges? We introduce electrons to just see if we can balance the charges, if they are positive or negative. So for example, if I have Fe going to Fe2 plus, the element Fe is balanced. But then if you look at the oxidation state for the product here is 0. Whilst at the reactant side, the ion is 0. The product side, the ion is +2. How do I balance it? Well, if I introduce 2 moves of electrons here, and electrons are negative charges, so meaning if I say 2 negative, then it is S2 minus plus 2 will give you 0. So on the left side, it is 0. On the right side, it is also 0. Does it make sense?
Yes, sir. Yes, sir.
Now, so this equation is balanced. Now I come to this equation. I balance the element. Chlorine is 2 here, chlorine is 1 here, so I put 2 here. The equation for the element is balanced. But if I check the oxidation state for the chlorine 2 here is 0. Now 2 minus 2. So that becomes minus 2. So it's minus 1 times 2. It is minus 2. So how do I balance the equation? If I put 2 electrons here, I'm going to be having minus 4. So it's better I put 2 here, 2 electrons, so that this side will be minus 2, this side will be minus 2. So this equation is also balanced. The last step is to put the half balance equations together. Are you following?
Yes, sir. Yes, sir.
Okay, so by putting them together, whatever I introduce must go off.
This
So,
week, my auntie name.
oh, please. So FE moving to FE2 plus 2 minus, and then I'm adding it to 2 minus plus Cl2, moving to 2 Cl minus. If I want to put everything together, there is 2 electrons here on my left side. When it crosses to my right, it becomes negative. So this will cross this one. So the electrons will cancel out. Then the final equation will be Fe plus Cl moving to the Fe2 plus 2 Cl minus.
Yes.
Does it make sense? Does it make sense?
Yes, sir.
So
Yes, sir.
the electrons which I introduce are just going to cross out. Well, a quick one. It means that, oh, please.
18%.
So it means that the chlorine that, I mean, the electrons that we introduce must be crossed out. So it's possible because this is positive, it crosses the arrow, it becomes negative, so we cancel that out. And so
Yes.
we should just note that redox reactions, we're going to be having a species which is losing and then another species which is gaining. So at the point when you see an equation which is a redox reaction, you should be able to spot that equation and note that it is a redox reaction or not. Can we figure some out? Let's see if the following will be a redox reaction before you balance that, because if it is not, it will be difficult to separate them into their half reactions, then you balance it. So I'm going to show you how you do the balancing very soon. Now let's see if these equations will be, say, potassium plus oxide giving you potassium oxide. Say calcium hydroxide decomposing to form calcium carbonate. Sorry, let me cross this. So calcium bicarbonate, not calcium hydroxide, calcium bicarbonate, producing calcium carbonate plus carbon dioxide plus water. And then the dichromate, okay, that's minus, plus a hydroxide, giving you the chromate. Well, if we balance that, that's CrO4 chromate plus water. Let's try to identify which one will be a redox reaction and which ones would not be a redox reaction. Can we do that? Well, how do we do that? We need to know the oxidation state. For example, if I take the first one, so the first equation. If I take the first equation, potassium at the reactant side is 0. And then if you calculate the oxidation state for potassium in potassium oxide, what is the oxidation state of the potassium here? Plus 4.
Yes.
4.
Yes. So potassium here was, so
Plus
from
4.
the reactant side, it was 0. And now potassium now is plus 4. So that means that it is going through oxidation. Do you agree?
Yes, sir.
Yes.
Now, if I take the oxygen here is 0, but the oxygen here is minus 2. So the oxygen 2 was 0. Here, the oxygen becomes minus 2. So sorry, it becomes minus 2. then you see that it is going through reduction. So clearly, this equation is a redox reaction.
Yes.
If I look at the two, yes.
Please, the charge for the oxygen was not shown at first. When you were writing the reduction state for the oxygen was when you added the -2.
No, oxide. Now this is potassium oxide. Oxide is having a charge of -2. Are you okay?
Yes, sir.
But when it forms a molecule, it has no charge. That is 0. Are you okay?
Yes, sir. Yes.
Okay. So in the potassium oxide, meaning the oxide is -2. That's how we could calculate the oxidation state for the potassium to know it's +5. Ideally, potassium should have oxidation state of +1. But then in this compound, potassium is having an oxidation state of +4. Okay. Now let's look at the other equation. When I take calcium, and then this bicarbonate is just mine. So this is calcium here will be +2 because of this exchange there. Okay. And here calcium is still +2. So nothing is happening. It's not undergoing oxidation. It's not undergoing reduction. Hydrogen here will be, so if I calculate that, hydrogen will be +1 here. Hydrogen is still +1 here. Nothing is happening.
Yes.
Oxide here is -2. Oxide here is -2. Oxide here is -2. Oxide here is -2. Nothing is happening. So this equation is not a redox reaction. In a redox reaction, so we can even only have reduction reaction. That is not redox. That one species is losing and that not the other species is not gaining. That is not redox. Redox is when one is losing, one is gaining. So for example, this case, one is losing, one is gaining. Now a situation where nothing is happening is not redox. Are you okay? Now let's consider this one. If I consider the chromium here, the oxide is -2 here. And so here it is still -2. Here it is still -2. Nothing is happening to the oxide. Now the chromium here, if you calculate the oxidation state, what will be the chromium here? So 2 chromium plus 7 times -2 to be equal to -2. So what's the oxidation state of the chromium?
14 in the
So 14 when it crossed there to be 12. So that's plus what?
+6.
+6. Now when we come here, what's the oxidation state of the chromium? So chromium plus 4 times -2 to be equal to -2. What's the oxidation state?
6.
+6. So you see, nothing is happening. So that is also not oxidation, a redox reaction. So basically, this equation, which is the K plus O2, which moves to KO2, is a redox reaction. Is that okay? Now, can you tell me which one will be the oxidizing agent? And which one is the reducing agent in this equation? So in this equation, which one is the... So the oxygen becomes the oxidizing agent, and then the potassium will become the reducing agent. That's correct. Why? Because it is going through oxidation, but then it is causing the oxygen to be reduced. Okay, so that's why it's an oxidizing agent. So again, when an equation is given to you, you don't just start saying that it is a redox reaction and then you start balancing that redox reaction. You need to really be careful to check whether there's oxidation going on and there is also reduction going on. Well, under redox reaction, before we, try to see where we start balancing that, is that there can be a situation where one species is losing and the same species again is gaining. In that case, that redox will say that it is a disproportional kind of a redox reaction. So disproportional redox reaction. It is losing and then it is also gaining at the same time. I give you an example so we can look at that. Say, for example, chlorine gas and then hydroxide meeting together will produce the hypochlorite and then the chloride and water. Now, if we want to separate that, we'll see that, well, here the hydroxide will clearly tell you that the oxides are just still going to be -2, 1. So here is +1 and then -2. So the oxides are off. Okay, but look at this, the chloride 2 here. The chloride 2 here moving to the hypochlorite. If you check the oxidation state, here it is 0. The chloride gas is 0. But here it is becoming +2 because oxide is -2. So that becomes +2. Do you see that?
Yes, sir.
Okay. Now, if you look at it again, well, the oxide and then the high is the same. Now, if you look at that, the same chloride now moving to that chloride. Here it is 0, here it is -1. Do you see that?
Yes.
So the same species, which is the chloride gas, is losing electrons. At the same time, it is gaining electrons. At this stage, it gains electron, it loses electron. At this stage, it gains electron. And this is an example of a redox reaction where the losing and the gaining is not proportional. It is disproportional reaction. Let me give you another example. So say Cu, so that is copper oxide, mix that with the, say, the proton to produce copper 0, and then the copper 2+, and of course, water. Now, this is going to be a +1, so that is just out +1. The oxide is -2 here, the oxide is -2. So what will be the charge here? What's the charge for this copper here?
+1.
+1.
Yes.
Okay. Now, if you look at it, this is out because it's +1. When it crosses the other, it's still +1. So the hydrogen is out. Now, look at this species, the copper oxide, or the copper plus copper 1 oxide, moving to copper 0. Here it is +1, but here it is 0. What has happened? It has gained electrons.
Yeah.
So that's reduction.
Yes.
So in this case, it is going through reduction. Now the same species, copper 1 oxide, moving to copper 2+. Here it is +1, here it is +2. So it has lost extra electrons. So such a reaction will say that it is a disproportional redox reaction. Are you okay?
Yes, sir.
So question.
Okay.
Yes, sir.
Yes, sir.
This with the disproportional reaction, which of them will be reducing agent and the reduction agent?
So the same species will be a reducing agent, the same species will be an oxidizing agent.
Okay,
The same species. That's why we are saying it's disproportional. It's not proportional where you can separate the the half equations and know this one is oxidation, this one. So the same species is going through oxidation and it's going through reduction. So that's why we call it disproportional reactions. Are we okay?
Yes, sir.
Yes, sir.
Okay. Then the next level is that once we can be able to identify redox reaction, then we have to try to see if we can balance the redox reaction. I'll initiate that, but then I don't think I can stop. I mean, I can finish, so I have to stop, and then we'll continue physically trying to see if we can balance redox reaction. Now, there's two approach of balancing redox reaction. I'm very sure one of the approach is well taught in the secondary school. The other approach, I don't see teachers teaching that, but that is the simplest approach. Okay, so two methods of trying to balance redox reaction. Number one is the oxidation state method. So the oxidation state method. And they don't really mention that in the secondary school, but that's quite simple. And that's you just want to identify the oxidation states of the element which is going through the oxidation, and the element, just the element. You isolate them from a compound. Then you balance that element and bring them back to the original form. You balance the equation. I'll show you then. Then there's a common one which they always use, which is the ion electron method. So the ion electron, where you introduce ions like the proton, that's the H plus, and then you introduce electrons. So you introduce ion, especially when you want to balance oxygen, you introduce water, and then the water on the opposite side will introduce H plus. That's a two method. Well, the disadvantages of the first method is that it can't tell you the state or the medium for the redox reaction. The redox reaction happens in mediums, either acidic medium, basic medium, or neutral medium. Acidic medium means that at the end of the reaction, there's an acid that is H plus in the system, or one of the species is an acid. That means that the redox is going through, it's happening in an acidic medium. The basic medium means that at the end of the reaction, there should be an OH there or ammonia. So one of the species should be an ammonia, or we should have OH minus in the system. That is a basic medium. Now, if I don't get H plus, I don't get OH minus or ammonia, then that is neutral medium. And so the first step cannot tell you which medium are you balancing the equation. And the second one tells you which medium. The ion electron method can tell you which medium are you balancing the equation, because at the end of it, you are going to be introducing H plus OH, so that it tells you whether it's in the acidic medium or the neutral medium. Are you okay?
Yes, sir.
I think you have a class after this, or we should proceed. So I'll just take one example and maybe use a two approach. Whichever approach that it's deemed fit for you, you use that. So remember, this will continue in the physical space. Any question? Any question, please?
Sir, please, can you repeat it again?
Which one?
The oxidation
and the
state
ion
method, the ion electron method.
So the oxidation, that's what I wanted to see. So let me pick one example, and then you just notice how you do that. So the oxidation state, you see in the redox reaction, we are dealing with compounds reacting together. So one compound reacting with another compound, but one compound is going through oxidation, then the other compound is going through reduction. Now in the oxidation state method, I only pick, so if you take the compound, it may be only just how do you call it? Only one element, not the entire element that is going through the oxidation. And it's not the entire compound that is going to reduction. Only one element is doing that. So we only pick that one element and balance it. Then when we balance that element, we'll bring it back to its original form in that compound. That's what we call the oxidation state method. That's quite straightforward. The only disadvantage is that it can't tell you whether it is acidic medium or basic medium. That's a disadvantage. But that's an easy way of balancing the redox reaction. Okay, now the ion electron, meaning you are going to be introducing ions such as H plus, OH minus, that's the ion, and they need to be balanced with electrons. So that's the ion electron method. So again, when we meet physically, then you can see how we do that. Okay. So then thank you very much, and then we'll see you next week.
You're welcome, sir.
Thank you, sir.
Okay, sir. You're welcome.
Thank you, sir.